Good afternoon. Welcome to the Fluid Structure Interaction and Solid Mechanics session of the 16th OpenFOAM Workshop Conference. I am Željko Tuković, and I'll be chairing this session. There will be 4 talks, and every speaker will have 10 minutes for their presentation, followed by 5 minutes for question and answers. First presentation is by Mr. Benedetto Di Paolo from IH Foundation Cantabria. Benedetto will talk about CFD coupling methodology for a realistic coastal engineering application. Please.
Okay, I'm going to share my screen. Can you see my screen and can you hear me?
Yes, we can see.
Okay, perfect. So thank you for your introduction. I'm Benedetto Di Paolo from IH Cantabria, and in this presentation I'll talk a little bit about CFD coupling methodology for realistic coastal engineering applications. So in many cases in wave structure interaction, as you can see in these pictures, the three-dimensionality of the flows occur around the structure, while are less important far away from the structure. So the main motivation of this work was to develop an efficient coupling methodology in order to properly deal with this phenomena, but in an efficient way. So we did an approximation of this for all of these cases, in which we developed the 2D, 3D coupling methodology. This methodology allows us to build into different domains in a multi-regional approach in OpenFOAM, which is a real powerful approach OpenFOAM has. We defined a non-overlapping scheme to couple the domains, and we defined also one-way and two-way coupling boundary conditions. We recently published this work. Here you have the papers. So the one-way coupling, what we do here is to sample the velocity field and the volume fraction inside in the bidimensional domain, and we transfer these fields to the 3D patch, which is an overlapping patch. So here we can transfer the flow information from 2D to 3D, and we also can absorb the reflected wave from the presence of due to the presence of any kind of structure. While on the other hand, we have the two-way coupling, which is derived from the Martinez-Ferrer et al. 2016. This scheme is derived from the discretization of the spatial terms of the generic transport equation. As you can see here on the right, by fixing the generic value of the variable and its gradient, we can couple the solution of the 2D region with the 3D ones in a two-way mode. So we started with several applications. The first one was highly nonlinear focused wave group interaction with a cylinder. This is a practical case, for instance, of wave interaction with monopile foundation of fixed wind turbines. And here you can see a comparison of a couple two-way simulation with a three-dimensional one. Here we correctly reproduce the three-dimensionality of the flow around the cylinder, as well as the plunging breaker along the planar pitch. Also, we compare the calculation of the horizontal force on the cylinder. As you can see here, we obtained a good comparison. All those small discrepancies are observed. However, the model is capable of catching the three-dimensionality of the flow. So increasing the complexity, we studied wave interaction with a in this case, a non-reflective breakwater. These kind of structures are used to reduce reflection in the navigation area and to produce calm water. So basically, here we reproduced our work published in Ocean Engineering. To do that, we built a 2D, 3D coupled domain, as you can see here on the right, where we forced the coupled interface really close to the three-dimensional structure in order to force the model where also the hypothesis of 2D, 3D flow cannot be assumed. So in this case, we studied several hydrodynamic cases, as you can see here in the table, by changing basically the wave period here. And we first calculated the wave reflection coefficient, which is one of the most important parameters when designing these kind of structures. As you can see, the two-way couple model here, and the results of the two-way couple models agree very well with both with laboratory data and also with the three-dimensional simulation performed by Wang et al. In 2019. So we continued our validation by comparing the pressure at the front wall of the structures, also outside the wave chamber used to dump the waves. And also we got good validation for pressure induced by waves. In this case, we also compared our results in the black lines with two-dimensional simulation, CFD simulation performed by Wang in the paper I showed you before. And in this case, we can see that the 2D modeling of this kind of structure fails in reproducing the complex three-dimensionality of the flow. Obviously, in that case, the three-dimensional geometry was assumed to be an equivalent porous media, but of course, all the three-dimensional flows around the structure are neglected in this way. So we also validated the velocity field inside and outside the cation. As you can see here, this is a cross-section of the structure. We measure velocity in the points V1 and V2, and also we compare the horizontal and vertical velocity for the cases we simulated. And also good comparison are shown here. The results was always below 10% of error. So also we performed a comparison between a one-way simulation and a two-way one. For these cases, I show you here a comparison of dynamic pressure of the pressure induced by waves at the front wall of the breakwater. As you can see, signal are almost coincident. So in this case, both models perform very well and are equivalent for this case. Also, the computational time is quite similar, as we are using the same multi-region approach, and the only things that changes here is the type of boundary conditions, which for the one way is a little bit slower, as we had to do many more calculations in order to, for instance, to absorb the reflective waves. So the last application was wave interaction with a dual wave energy converter inside a breakwater. In this case, we combine an oscillating water column and an overtopping based device called OBREC inside an existing vertical breakwater. This was under a European project called Seaports, where we applied the model we developed successfully. For instance, here I show you the pressure induced by irregular waves at here inside this small reservoir on the top of the breakwater. As you can see, both signal from the two-way couple model and the laboratory data are in phase. and also the amplitude of the oscillation agree very well. Here, finally, I show you several more applications, not only for coastal engineering cases, but also, for instance, on the right, on the top on the right, you can see wave interaction with an intake tower for nuclear power plants. Also, this case has also been validated. Here on the bottom, you can see a tsunami inundation with several structures and tanks. Also, another case we validated, also wave breaking on a planar beach, on a planar porous beach, where we can see the three-dimensionality of the flow confined in what we call near field. Where we have the presence of the structure. We can also see how waves are percolating inside this porous material. And the previous case I showed you in the validation cases are these cases. For instance, as you can see here, waves are interacting with the dual wave energy converters, and you can see the oscillation inside the oscillating water column, the overtopping device, which are impacting the structures, also are entering some pipes, and then the overtopping discharge is filling this tank outside the breakwater. So we validated our model for all these complex cases, and now we are including a new method for active absorbing the reflective waves, which is a new method in order to improve the capabilities of the existing numerical CFD numerical models for the active wave absorption. In this method, we used a near field method based on digital filtering. We implemented it in the OpenFOAM platform, and is based on moving boundary method. So to conclude, the coupled models have been validated against experimental data in 3D simulations. Also, the performance of the coupled models are comparable to three-dimensional simulations and experimental data. The computational time is strongly reduced, allowing to avoid the use of simplified models, for instance, the potential flow solvers. And all the realistic cases we simulated only took a few days to finish the simulation, to complete the simulations in a normal computer desktop, which means without using HPC resources, which could allow us to extensively use these kind of techniques for industrial applications. So thank you for your attention.
Thank you very much for a nice presentation. We have time maybe for one or two questions. We have one question from Mr. Babai, who asks, in your FSI work, is your structure deformable?
Well, all these cases are based on fixed structures, but of course the coupled solvers allow us to study the moving structure, for instance, not deformable structure. In order to do deformable structure, we should couple. Our solver to, for instance, an FSI solver, like solids for foam.
So this is not FSI?
No, it's not FSI.
But why are you mentioning one-way coupling then, or two-way coupling?
No, with one-way coupling or two-way coupling, I meant the directionality of the flow. For instance, with one-way coupling, we transfer flow information from 2D to 3D, and with the two-way one, we transfer information from 2D to 3D, and vice versa.
Okay.
The one.
And
no, it's not an FSI. It would be interesting in the future to couple this with many other solvers, because it's based on the multi-region approach, so it's easy to maintain, to extend, to implement new physics. So yeah.
And can you explain a little bit this term digital filtering? This is another question. What does it mean?
Okay. Yeah. Well, this is based on laboratory theory for wave makers. It's what we do normally in laboratory experiment in numerical facility for instance, in the wave tanks and basins. So by digital filtering, we designed a digital filtering to approximate a transfer function in order to absorb waves. It comes from the theory, and then we developed a filter design method.
Okay.
Starting from the filter design method, we implemented basically what we do here in OpenFOAM is to implement a convolution.
Okay.
A new boundary condition for a moving boundary based on a convolution in order to absorb waves.
Okay.
And yeah.
Thank you very much. I think we do not have enough time. We can continue this discussion later after the session.
Okay, I'll stop sharing. Thank you.
Okay.
Bye.
Bye. So second presentation is by Mr. Iago Oliveira from Sao Paulo State University. Mr. Oliveira will talk about semi-coupled numerical strategy to solve large strain motion of incompressible hyperelastic material. Mr. Oliveira, can you share the screen?
Sure. Can you see it?
Yeah, we can see. Yep.
Okay, thank you. Thank you, Professor Dujkovic, for the introduction. So I'm going to talk about a semi-coupled numerical strategy to solve large strain motion of hyperelastic materials. Before that, I think it's always important to introduce where we come from. So I'm from São Paulo State University in Brazil, in the state of São Paulo, and I'm doing my PhD here in working in the simulation of intracranial aneurysms, of FSI and intracranial aneurysms, and together with, in a partnership with the Albert Einstein Hospital in São Paulo and Dalhousie University in Canada. We're currently funded by FAPESP, the São Paulo Research Foundation, and this particular work that I'm going to present today, I did last year when I was working with Professor Cardiff in Dublin. So what this work is about, the main motivation is to solve the motion of incompressible materials, which are characterized by a Poisson coefficient equal to 0.5 or nearly incompressible that tends to 0.5. And although in engineering, the most common materials are have a Poisson coefficient between 0.2 to 0.5. There are some applications for incompressible materials, for example, with rubber-like ones, such as elastomers and materials in inelastic conditions. And more specifically, with the type of material that we are interested, such as soft tissues like arteries, which also are incompressible, and also the tissue of intracranial aneurysms. And what is the problems, the main problems when simulating and numerically solving the motion of these materials? So one of them is because of volumetric locking, when that causes the deterioration of the performance of the solver, of classical solvers based on a displacement formulation. So for example, if we get this example of a benchmark of a plate with a hole and loaded axially, and we simulate that with the displacement-based solver, we get this convergence behavior as the Poisson coefficient goes to 0.5. So the convergence gets deteriorated and the number of iterations increase a lot as the nu tends to 0.5. Furthermore, even if we get a convergent solution, we may have some unrealistic oscillations in the stresses of the solution. So our work is based in others, of course, and we're going to give a little background here of what is available in the literature with the finite volume method in this case. Of course, there are a lot of other studies with the finite element method. And it basically started with two works in 2005 and 2006, where the authors, they used the finite volume method to solve small strain and large strain problems, but using a displacement-based algorithm. And more recently, the same authors, they proposed what they call the mixed formulation, of the finite volume method to solve small strain, but with a decoupling of the momentum equation to improve the convergence of the solver. More recently, in a presentation in the same workshop in 2019, the same methodology was applied and implemented with a block-coupled framework of foam extend, but with small strain problems, which brings us to our goal, that is to use the similar mixed finite volume method with the block-coupled framework in foam extend, but actually to solve large strain problems of hyperelastic materials. Thinking mainly to solve the intracranial aneurysm motion, specifically in this case. Our starting point is the momentum equation in the total Lagrangian formulation, where sigma is the Cauchy stress and JF are the deformation gradient. And I won't go into all the details of the mathematical manipulations we do with this equation in the implementation, but to avoid the discretization of the whole nonlinear term, because we are supposing this sigma is nonlinear, we add in a deferred correction manner two terms in the momentum equation, in which sigma h is the Hookean law, where we introduced the pressure given by the small strain law, kappa times the divergence of displacement, based on the mixed formulation of the authors that I mentioned before, where kappa is the book modulus, which controls the compressibility. And we do that to avoid the whole discretization of this term, because then we can discretize implicitly part of this term, improving the formulation. And the sigma then holds the constitutive law that we are actually solving. So after integrating this equation in a control volume, the momentum equation, there are much more terms here, many more terms here, of course, but I won't explain all of them. We basically do that to improve the implicitness of the discretization. After integrating and discretizing this equation using the finite volume method, we get from the momentum equation one equation for the solid displacement, but coupled with the pressure here, which comes from this definition of the pressure. And all the other terms are discretized explicitly. And the same manner for we integrate the pressure equation in the finite volume and discretize it, obtaining this discretized equation for pressure, which also involves the displacement and some extra terms due to the Richau correction added. So these two discretized equations, discretized momentum equation and the discretized pressure equation, they are, instead of solving them separately as is traditionally do it in displacement-based and segregated solvers, we solve them in a block-coupled manner using the block-coupled formulation of foam extend, where the two equations are assembled together and we have a system for each cell, which are solved together for displacement and pressure. This solver is currently implemented in solids for foam in a particular solid model, so it allows us to use the different material laws that are implemented in solids for foam too, and also to be used in fluid-solid interaction solvers, for example, if that is desired. But it's still a little preliminary, this work. So to show what the solver is capable of, I'm going to present two numerical experiments here. One, the uniaxial extension problem. We use that because it's a simple cube-like geometry that is stretched in one direction, and we use that because there is an analytical solution available for different hyperelastic laws and a cylinder pressure vessel. So the first one, the cylinder with a 9 pressure, is a thick cylinder where we assume that it's made of a new Hookean model with constants that would give us a small strain solution, just to verify that the code gives the correct solution for a small strain, which is necessary. So compare the radial stress and the hoop stress for this case. We see that we compared our semi-coupled strategy and the classical segregated one also implemented in solids for foam. And we see they both agree quite well with the analytical solution. But the semi-coupled one does not present the oscillations that the segregated solution exhibit, which we only manage to eliminate only by refining the mesh. And regarding performance, the segregated one displays the same behavior that I showed before, where the convergence gets deteriorated, whereas the semi-coupled one, it displays a consistent behavior as we increase the Poisson ratio to achieve the nearly incompressible behavior. And the other benchmark was the uniaxial extension one. So it's just a cube that is stretched along a direction. And we have the analytical solution for this benchmark for different material laws. So we employ the Money-Rivlin, the Aoi, the Fung models, which are traditional models used to model arteries and intracranial energies specifically. So regarding the solver, it shows the good agreement with the analytical solution independently of the models that we tested, as you can see in this figure, of the stretch strain curve for this case. And the residual behavior is pretty much the same that I showed you before from cylinders. So the semi-coupled one shows a pretty much consistent behavior independently of the Poisson coefficient, whereas the segregated one deteriorates completely, even for these very simple cases. So to conclude, so we showed that the mixed formulation with the block coupled one, it still seems to be good to solve the large strain problems of different hyperelastic materials. And it presents a consistent convergence behavior through a range of different Poisson coefficients. And furthermore, the pressure oscillations that we verify in the segregated solutions, they were not detected, at least in these cases that we simulated. And this work is still preliminary. We are developing, still try to get it better, the solver that are currently implemented, but it is implemented in solids per foam in the development branch. So anyone who wants to use it may help, of course. And for further works, I'm going to try to use the solver for other problems like the aneurysm that I mentioned, and for different problems, of course. So thanks for the attention, and I'm open for any questions.
Okay, thank you very much for your presentation. So we have time for one or two questions. For example, you mentioned that with segregated, you have pressure oscillations or solution oscillation, and with semi-coupled. What do you mean by semi-coupled?
Oh yeah, I forgot to mention that we didn't use the coupled. We used semi-coupled because we didn't discretize the whole nonlinear term. So we didn't include the whole discretization of the intercoupling between the components of displacement, but we used the block coupled framework to implement it. So that's why it was a semi-coupled one.
So my opinion is that solution procedure should not influence or affect the solution, but solution procedure, for example, coupled or segregated. So at the end, you should get same solution if your discretization is same for both solution procedure. So
in this case, sorry.
Yep.
I was going to say that what we saw in the displacement based, well, as far as I talked with Professor Cardiff, was more related to it may appear near the boundaries, and the reach-out correction may help with the oscillations, at least in the segregated solver, and also, but for that case specifically, the only way that I found to at least to dampen the oscillations for that case was to refine the mesh. Even using the reach-out correction with some level, it didn't improve very much the solution, at least. So it may happen, but for all the cases, at least when we approach the nearly incompressible behavior, the convergence deteriorates with the segregated solution that are traditionally used.
Okay, thank you very much. So we can conclude with your presentation, and if you can On share screen, yeah. Okay, so third presentation is by Dr. Sauba Mohammadi from Chalmers University of Technology. Dr. Mohammadi will talk about fluid structure interaction on a fixed fan blade.
Hello, everyone. My name is Saber Mohammadi, and I'm here to give a presentation on fluid structure interaction on a fixed fan blade. This is a presentation outline. I'm starting with introduction and then case study and CFD result, then simplification for FSI simulation, simulation results, and then conclusions. A fluid structure problem is defined by a set of governing equations to be fulfilled in the fluid and solid domains, plus suitable coupling conditions, ensuring the continuity of velocity and normal stress across the fluid-solid interface. We can divide FSI problems into partition methods and monolithic ones. In partition methods, the solid and fluid domains are solved separately by using one's favorite numerical method and possibly non-matching computational grids. Partition methods can be divided into strongly coupled schemes, which enforce discrete counterpart of both coupling conditions up to a tolerance of choice, and weakly or loosely coupled, for which the coupling conditions are not exactly satisfied at each time step. In monolithic approach, one deals with the coupled problem as one whole by adopting a unique strategy. Monolithic methods are strongly coupled as well. In this research, the strongly coupled partition method is being used based on finite volume method for both solid and fluid. Axial ventilation by use of axial fans was the most common cooling concept for hydropower generators in Sweden. They are still being used when some old generators are being refurbished, especially in rotary machines. The design of fans, which is used in the main part of hydropower generators, are made by bended plates, which are welded on a fan ring or segment to keep the cost at minimum. They operate in airflow that is highly restricted to the space that is available when the electromagnetic parts of the machine have been designed. And therefore, they don't have ideal flow angles close to the blades. Then for this condition, it is necessary to study fluid-solid interaction on the blades to be able to avoid fan blades failure. Here you see a broken fan blade at the right down picture. This broken fan blade may cause severe damage to other parts of the machine. This is a computational domain of the ventilation part of a hydropower generator. At left, you see the flow direction and some of boundary conditions that we have applied in our simulation. At the right, you see streamlines. You see they are complex at the upstream of the blades, and again close to the blades, which are quite blue. You see there is a complex and chaotic flow inside the machine. Here at the right down picture, you see isosurfaces of Q criterion, which shows turbulent structures around the fan blades. They are the causes of unsteadiness and also some fluctuations on the force that you see at the top picture. This is the time history. This is the history of force. That you see that there is lots of fluctuations on the force, which are because of the vertical structure. At the left picture, you see a midsection of the blade in our computational domain. You see here relative flow arrows. These arrows and this plane is colored by relative velocity itself. You see here, it's obvious that at this section, they are approximately aligned with the chord line, as you see here, with the chord line of this fan blade. It shows that they enter directly to the fan blade and they don't have any special angle of attack to this blade at this section. The aim of this research is to study the FSI behavior of fan blade and validate the result using experimental tests. Therefore, we need to design a setup to be able to implement both numerically and experimentally. So we needed to consider the fan blade in fixed frame to be able to achieve all our goals. Here at the left picture, you can see all radial sections of fan from root to tip. You see they are producing approximately equal amount of thrust at each section. Therefore, considering the mid-plane of the blade is the best choice to tune the angle of the entering flow and also the velocity, relative velocity of the flow, which we want to use as inlet condition. You see here at the central picture, you see we have placed the blade with this zero angle of attack and with the velocity equal to 57 meters per second, which is equal to the relative velocity at the center of the blade, as you saw in the previous slide. And we are using the channel. The side spacing is equal to the half interblade distance. We kept the tip clearance at the top of the blade for our experiment and also for our simulation. You see here the design and build setup at Chalmers Laboratory of Fluids and Thermal Science based on our introduced domain. We are doing experimental tests on this blade to measure shedding frequencies and also vibration of the blade. Here are some general information about our FSI simulation. The fluid-solid interaction is solved using SolidForFOAM in this research, which is an open source module for OpenFOAM, which includes the solid, fluid, and also fluid-solid interaction solver. We have compiled it on our clusters using OpenFOAM version 1912. We are doing an SSD simulation using SSP SAS turbulence model to be able to capture vortex shedding with a combination of moderate computational cost and also acceptable accuracy. Our fluid-solid interface is ITCAN method, and our transfer method is AMI because we are using non-conformal interface meshes. As you see at the left picture, we are using a fine mesh in fluid, and at the right picture, we are using a coarse one in solid domain. We started a fluid-only simulation using SolidForFOAM to be able to get some information about the flow and also vortex shedding to be able to have a better insight into our problem in FSI part. It is obvious that we are having separations at the backside of the blade, close to the tip and also behind the trailing edge, which would be the sources of vibration. These turbulent structures you see at the right down picture in isosurfaces of Q, which are turbulent structures on the blade. We have done some sampling on pressure close to the tip and behind the trailing edge to be able to get some shedding frequencies to see what are the dominant frequencies in our fluid domain. Here are FSI results for our simulations. We see approximately similar turbulent structures around the blade. Moreover, at the right, you can see the exaggerated deformation of the blade by time due to flow unsteadinesses, and the maximum deflection has been 1/10 of a millimeter in our simulation. In our FSI simulation, we have done some sampling on the pressure, some pressure sampling to get shedding frequency, and we have done some finite Fourier transform to extract the dominant band. Moreover, you see at the mid picture. Moreover, at the right, you see the deflection history of the blade's tip. It is observable that in both pictures I have mentioned here underneath the picture of the deformation that we have a 145 hertz frequency for the deflection of our solid geometry, and we have a shedding frequency of 143 hertz in our fluid part, which can be a sign of locking since both of these frequencies are close. But these frequencies are about 10% higher than the blade's first natural frequency. In our simulation, you see the blade natural frequencies at the left. The first one is 134. The question is, how far should we be from the natural frequency? Some companies choose 20%. To have a better insight, at the left, you see a sample graph from one of our references. Here, you see if a load is applied dynamically on a geometry and solid, the deflection is around 75 times the deflection of the geometry by applying the equal static load. If we have 10% safety factor in our design, the deflection is 5 times the static deflection. The question is, how accurate is our extracted natural frequency and also our solid frequency extracted from FSI? Is it possible that we get some resonance in our geometry, physically or in our simulations? We should find our answers by comparing our results with experimental data, which is under progress. Moreover, for our future work, we are running some LES simulations to be able to get more accuracy on extracted frequencies. In this research, simulations were done on the ventilation system of a hydropower generator. The geometry was simplified to be able to do FSI simulation and experimental tests. FSI simulations were done using solids for foam, and dynamic response of the blade shows that it might be vulnerable to resonance. More details about this research would be given at Gutenberg Region OpenFOAM user group meeting at 18th of June. You can contact Professor Håkan Nilsson to get invitation link to this meeting. Yeah, thank you for your attention, and I'm here for any question.
Okay, thank you very much for your nice presentation. I have one question. Yeah. So I see that your blade is very thin, and I would expect that you will have problem with convergence on solid side. What solver did you use for solid side?
For solid side, we are using, we tried different options. Actually, there were some fluctuations on our solid when we were doing FSI simulations. And now we are using Eulerian solver in our solid part. It's it's available in solids for foam. And yeah, it's good. It's better than based on our experience. We are getting more stable results using Euler than backward solver.
No. I mean, what kind of solver in terms of solution procedure? Do you use segregated or coupled?
Yeah, we are using segregated.
Segregated procedure. Yeah. Okay. So there is one question related to turbulence model.
Yeah.
So, question is, how do you think the turbulence model is acceptable for this case? Have you argumented this?
Actually, we have done some studies on our turbulence model. We are doing some experiments to find how accurate is our turbulence model. But based on our experience, we have tried SST SAS, which is good for based on RAND, URAND, the method, which is suitable for to get shading frequencies. But on the other hand, we are doing some LES simulations, and we get quite compatible results using SAS and LES. That I think it should be a good turbulence model for simulations.
Okay, thank you very much. There are much more questions. Please check this question queue later and try to answer the questions. And now I would like to ask you to stop sharing the screen so that we can continue the next presentation.
Yeah, thank you so much.
Okay, fourth and last presentation is by Mr. Luka Balatines from Faculty of Mechanical Engineering and Naval Architecture, University of Zagreb. Luka will talk about analysis of lubricated point contact using the finite area method. Luka.
Hello, I hope everyone can hear me all right.
Hello.
Yes, hi. So just a moment, let me share my screen. Okay, so can everybody see the presentation?
We can see you.
Okay, thank you. So, Professor Tukovic, thank you for introduction. As was already said, my name is Luka Balatines, and for the next few minutes, I'm going to talk about the lubricated point contact model developed in our group. So this presentation consists of 4 sections. You can see them here, and it's going to focus on the lubricated point contact model developed as part of a numerical framework used for metal forming and wire rolling simulations. So we know that experimental tests are used as standard practice in various industries. They are used for metal forming, wire manufacturing, bearing design, and so on. And we also know that they are quite time-demanding, costly, and usually trial and error based methods which rely on physical models. On the other hand, numerical modeling emerged as a cost-effective alternative to experimental methods, and with the advancement of computational resources and the development of more complex numerical contact models, greater accuracy was achieved. This means that numerical methods became a viable design tool, or can be used as an add-on to existing tools to better focus on microscopic contacts and friction. So this brings us to our goal. Our goal was to development of a numerical framework based on the finite area method to be used as a viable tool for simulations of lubricated contact of rough surfaces. So we wanted to focus on lubrication, friction, and heat transfer, as those are very important factors in metal forming. And if any of these factors is left unoptimized, this can lead to severe degradation of the quality of the final product. So to reach our goal, we needed a reliable and efficient numerical model for lubricated contact, which is able to take into account both different lubrication regimes, different surface topologies, rheological changes to the properties of the lubricant, and heat transfer. The heat transfer part includes both solid-to-solid heat transfer and solid-to-fluid heat transfer. So we successfully developed, implemented, and validated the model, and all the information can be found in Mr. Škurić's PhD reference here. Our final goal was to use the developed model as a boundary condition for a large strain hyperelastoplastic finite volume deformation solver developed by Cardiff et al. So our lubrication model, our lubricated point contact model needs to be applicable to all 3 main lubrication regimes. This includes both thick hydrodynamic regime, where smooth surfaces can be assumed, and the thin hydrodynamic regime, where the surfaces are a bit closer together and the surface roughness starts to affect the lubricant flow. Also needs to be applicable to the mixed lubrication regime, where the surface contact pressure is shared between the asperities in contact and the lubricant. Lastly, it also needs to be applicable to the boundary lubrication regime, where all of the contact pressure is carried by the asperities in contact. This means that our lubricated contact model needs to be able to accurately describe both solid-to-solid contact and solid-to-fluid contact. Also, it needs to be able to couple the two to be able to accurately describe the mixed lubrication regime. So the lubricant flow in our model is described by a modified Reynolds equation. This is a partial differential equation which governs the pressure distribution of the viscous fluid films, meaning our lubricant flow. It needs to be valid for all lubrication regimes, and this modified Reynolds equation was discretized using the finite area method, which is a two-dimensional counterpart of the finite volume method. Here we can see a pressure-based form of the modified Reynolds equation, but if you are interested in the derivation of the equation and a discussion of the physical meaning of certain terms, please check the references given below. So we had to take into account a few assumptions. Firstly, we assume that viscous forces dominate over the fluid body, meaning that both inertia and surface tension are neglected. Then any fluid film curvature can be neglected because the overall thickness of the fluid film is smaller than the width or the length of the film, and any variations of the pressure across the fluid film can be considered negligibly small. So by introducing flow factors as correction factors for the modified Reynolds equation, the equation is able to calculate thin film flows between rough surfaces, and the flow factors by themselves are calculated via analytical equations, which depend on the film thickness at certain computational points. So we already mentioned that in the mixed and bundle lubrication regimes, the contact pressure and the shear stress are shared between the asperities in contact and the lubricant. And our methodology, our framework, uses a ratio called A. This is the ratio of the asperity contact area to the unit normal area to calculate both the normal surface contact pressure and the total surface shear traction. This means that we need to be able to accurately assess A. And for that, we need a very good asperity contact model. We already know that usually there are two types of asperity contact models used. First, we have the statistical contact models, which do not take into account asperity interaction. They are usually based on the single hemispherical asperity with a single average radius, and usually assume Gaussian distribution. This means that they could be problematic as different topologies tend to produce same results. This is why our lubricated point contact model is based on a deterministic, elastic, perfect plastic contact model based on the procedure introduced by Sachen et al. And Stanley and Cato. This means that it uses direct measurements of surface topology for calculating both film thickness, area ratios, and contact pressures. Moving on to temperature models. So our model uses two different temperature models. First, for the surface temperature, it uses a moving heat source equation with fast Fourier transfer for faster calculation. Then the lubricant field temperature is calculated using a 2D energy equation, which assumes a parabolic temperature profile across the film thickness. Now to talk about the validation cases, our lubricated point contact model is validated on 2 point contact cases. Both of them are based on a ball and disc turbometer, but for different lubrication conditions. The numerical results are compared to both numerical and experimental data found in the literature. And here we can see the two test cases used. Both of the cases are named after the lubricants used in the case. First, we have the Turbo T9 oil, which is used to validate purely hydrodynamic regimes for different loads and different entrainment speeds. And then we have the Turbo T68 oil, used to validate both mixed and bundle lubrication for different surface specimens and different types of roughness profiles, both the measured and approximated roughness profile. Here we can see the results for the Turbo T9 case. On the left side, you can see film thickness versus entrainment speeds, both for our numerical results and for the experimental results found in the literature. We can see both the results for a minimum film thickness and a central film thickness. And we can see very good agreement with the experimental results from the literature. On the right side, we have the friction coefficients results versus the slide to roll ratio for both our current work and the simulated experimental data from the literature. We can see excellent agreement for 0.8 meters per second entrainment speeds, but as we move into higher values of the entrainment speeds, we can see some discrepancies. Those discrepancies were expected due to some simplifications we made. Those are the temperature profile, which we use two-dimensional temperature profile, while the numerical data from the literature use a three-dimensional temperature profile. And we also used average values of the density and viscosity, while the values used in the numerical model from the literature were numerically integrated. Those are necessary simplifications that we had to use due to our two-dimensional film discretization over a contact patch. Here we can see the hydrodynamic pressure field for pure rolling conditions and a single load. We can see as we increase the values of the entrainment speeds, we can see an elongation of the pressure field, and also we can notice sharp high pressure edges at the exit of the contact. Here we can see the film temperature field for the turbo T9 case for different entrainment speeds, for two different entrainment speeds and different slide to roll ratios and a single load. We can notice that for higher entrainment speeds, the overall, we can achieve overall higher temperatures, and we tend to have longer high temperature trails after the film exits contact. Similarly, by increasing the slide to roll ratio, we also get higher film temperatures, but we also get a larger high temperature region. Also, it is interesting to note that we can see a high temperature front, but this is due to the high pressure front seen here. And lastly, we can see the results for the turbo T68 case. We can see the results for the friction coefficients versus entrainment speeds for both for the experimental results and for our numerical results with the measured surface roughness profile, even with the approximated surface roughness profile. Generally, we have fair agreement with experimental data, but we need to know that the measured surface roughness profile produces better results than the approximated one. And the slight discrepancies seen here when compared to the experimental data are attributed to the lack of available transport properties for the T68 oil. For the T9 oil, we had all the necessary transfer properties, but for the T68 oil, we only had a few data points. Here we can see temperature fields for three different values of the entrainment speeds and a single slide to roll ratio. And we can notice that on the left for the hydrodynamic regime, as we start to lower the entrainment speeds, the temperature of the lubricant will start to decrease. But then if we move into the mixed and boundary lubrication and start to lower this, continue to lower the entrainment speeds, the ratio of the boundary contact will increase, and we will achieve higher temperatures. Similarly, as we continue into the boundary lubrication regime, but continue to lower this entrainment speeds to smaller values, the speed between the ball and the disc will decrease, and we will have a decrease in the film temperature. So to conclude, we implemented and validated a lubricated point contact model, which uses a modified Reynolds equation with flow factors and is thus applicable to all lubrication regimes. It also relies on a deterministic contact model, which is able to take into account real surface topography. And we validated the model using experimental and numerical data from the literature, showing very good results, but greater accuracy can be achieved if detailed transfer properties are available. Lastly, our future work will focus on the implementation of a lubricated contact wear model. So thank you for your attention. Please feel free to ask any questions. And for those interested, here are the references cited in the presentation. Thank you.
Thank you very much, Luka. We have time for a few questions. So there is one question from the audience. Are there any assumptions on the numerical models that do not resemble the experimental conditions?
So this was used to mimic the experimental data as close as possible, so we could perform the validation. But as I said, this is a part of a larger framework, which is used for larger and more complex simulations of metal rolling and metal forming and wire rolling.
Okay, thanks. So maybe one question from my side. Would it be possible to analyze your problem as a conventional fluid structure interaction problem.
Well,
and do you plan to do that?
We plan to focus on the very modeling part next, but I suppose it could be modeled that way.
Okay. So no more questions from audience. I suppose we can finalize this session. So you can stop sharing the screen.
Okay.
So at the end, I would like to thank speakers for their contributions and of course audience for their attendance. Goodbye and see you on next fluid structure interaction session tomorrow. Bye.